So now, how do we set up? Let's talk about setting up a d rho d theta d phi integral. So we'll follow that order. How do we do this? Well, as step one, we should think about the inner integral as usual first, right? So we should be thinking about the bounds for rho. So that is, rho should be sandwiched between something and something. And kind of as usual, it can mention a later variable. So you can use either theta or phi. You don't have to, but if it makes sense to, you can mention one or both of those. So there are, further steps, but I think the steps are going to be fairly natural as we try going through an example. So what I'd like to do is I'd like to set up an integral in spherical coordinates. For the integral of f of x comma y comma z equals xz over the solid sphere of radius 9. Now, before we really get going, I would just like to comment that previously we discussed this problem and did this in cylindrical coordinates. So I just would like to recall an answer from just a very recent class day, just a little earlier. We had integral 0 to 2 pi, integral 0 to 9, integral negative root 81 minus r squared to root 81 minus r squared of r cosine theta times z, and then r dz dr d theta. So we had previously written in cylindrical coordinates this way. Now, for doing this as a d rho d theta d phi integral, let's talk about how would this be different. Yeah, for this, well, we should figure out bounds for rho, and then once we've figured out bounds for rho, we should figure out bounds for theta. Theta should be between what and what. And theta can mention phi if we want, and then phi itself needs to be bounded by constants. But let's think through what's going on here. We've got a solid sphere of radius 9. So, values of rho, again, rho is the straight line distance for a point to the origin, so that should be 0 to 9. Get just points of any distance from the origin between 0 and 9. Theta? What values of theta do we want? Well, we want to go all the way around, so this should be 0 to 2 pi. Remember, theta is just moving around in the xy plane only, so we want all of that. And then phi, well, we want the entire sphere, right? So 0 to pi. These are all the possible values. Recall that phi goes between 0 and pi only. You can't have phi larger than pi. And yeah, we'll see in a moment what happens if we don't have phi going from 0 to pi. And then what about the function? It was x times z, and if we just take from earlier, x was rho times sine of phi times cosine of theta, and then z, recall earlier, was rho times cosine of phi. So, to set up an integral sign, integral sign, integral sign. Actually, these integrals don't even need to be spaced that far apart because all of the bounds are really tiny to write, even compared to this bound that we had to write in cylindrical coordinates. Let's just leave some space here. Let's write the replacement for xz. So let's write this, the integrand, in place here. So rho sine phi cosine theta, and then z got replaced with rho cosine phi. And then dv is rho squared sine phi d rho d theta d phi. Let me just maybe underline here this part, that whole thingy here is dv. So we just need to list bounds for rho on the innermost integral. So looking over here, 0 to 9. Then bounds for theta, 0 to 2 pi. And then finally bounds for phi, 0 to pi. Okay, the question just said set up, so we're actually done. Now, you might question why phi goes from 0 to pi. Maybe you're thinking phi only goes from 0 to pi over 2. You might be questioning why theta goes from 0 to 2 pi. Why not just 0 to pi? Or why not pi to 2 pi? Or so on and so forth. So some of the next examples we're looking at are meant to help with understanding that. So stay tuned.